So the second derivative test, not to be confused with using the second derivative for concave up and concave down. The second derivative test is an additional test to find out if something's a maximum or a minimum. The first derivative test was where you found out your derivative 0, and if you do then increasing, then decreasing, then increasing, then you could say things were maximums and minimums. The second derivative test uses the second derivative, but again, it finds out if something is a maximum or minimum. So the first thing in the second derivative test is you still have to find the first derivative is equal to 0. That's the same in the first derivative test and the second derivative test. But in the second derivative test, you then look at the second derivative. So the second thing that you do is you look at your second derivative at that point. So what it says is if my first derivative is equal to 0. So here's a minimum point. Can you see there at that point it would be equal to 0, your first derivative, because the tangent would be horizontal. And the second derivative, if you plug the second derivative at that point C, you would get a positive number because it's concave up at that point. And if the first derivative is 0 and it's concave up, the only possibility is it's a minimum. If it's equal to 0, and it's concave down, then it has to be a maximum. So if the first derivative is equal to 0 and the second derivative is negative, then the only possibility is that it's a local minimum. And this is called the second derivative test. So let's look at an example. Okay? Find the coordinates of the local maximum and the local minimum of this, and the inflection point of this function, and use the second derivative test to show their local maximums and local minimums. So first of all, if I want to find maximums and minimums, I need to find my derivative, which will be 3x squared minus 12. I set my derivative equal to 0. I'm going to factor out a 3. Okay? So I know it's equal to 0 at negative 2 and 2. Normally, we would put negative 2 and 2 into here and find out increasing and decreasing. And that would tell us if they are maximums and minimums. Okay? Right now, I'm going to temporarily, although it feels wrong, I'm going to skip that step. So we have to use the second derivative test. My second derivative is equal to 6x, right? And using the second derivative test, at x equals negative 2, f prime of negative 2 is equal to 0, and f double prime of negative 2, if I plug in negative 2 into my second derivative, I get negative 12, which means it is concave down at x equals negative 2. So I know that that point is going to be a maximum. If I want to find the y-coordinate of that point, I have to plug -2 back into my original equation. -8 plus 24 plus 5, 21. So what the second derivative test can do for you is if you just want to quickly find a max or a min, you just have to plug in two values. You have to find out where your derivative is equal to 0, and then just quickly plug that value into your second derivative, and you can tell right away if it's a maximum or a minimum. Most often, though, when we do our curve sketching, we do our first derivative test naturally as part of the graph, and so we almost always skip the second derivative test. So let's finish the second derivative test, because we just found out one point was a maximum. The other value at x equals 2, we know that f prime of 2 is equal to 0, and f double prime of 2 would equal positive 12, which means it is concave up. And sometimes I even like to draw these faces above the number, because if you draw concave up like that, then you can easily see that it is a minimum, because it would have to be this point right there. If it's concave up, it has to be a minimum. How do I find the value? It's going to be 2 comma something. Again, I go back to my original equation. 2 cubed is 8, minus 24, negative 16, plus 5, negative 11. Hey. So there we use the second derivative test. Now, what haven't we done? We could double check it with the first derivative test if you plugged a number into f prime, right? Something less than -2. This is going to be a negative times a negative. This is positive, meaning it's increasing. If I plug in 0 into my derivative, I get a negative, which is decreasing. Did we find out that at -2 we had a local maximum? Yes, we did. If we plug in something larger than 2, it's positive again, increasing. Did we find out at positive 2 it was a minimum? Yes. Okay? That's the first derivative test. So I tried not to do it right away, because we're supposed to do the second derivative test.
Is the reason for the second one that it's concave down is because it's like a negative?
Yes. So the reason that this one's concave down is because the second derivative is negative. So right beside here, I'm going to draw my number line for the second derivative, and I'm going to use the second derivative to find concavity, but it's not the second derivative test. Drawing that number line isn't the second derivative test. And then plugging something in here, this is negative, everything here is concave down. This is positive, everything's concave up. Again, I'm plugging things into my second derivative to find concavity, but that's not the second derivative test. Both the first derivative test and the second derivative test find maximums and minimums. They both find the same thing. So you don't need to do both of them. And most times when students are graphing, they do the first derivative test right away. There's no need to do the second derivative test. But sometimes questions come up that say, can you show me you know the second derivative test? And that's what we're doing today. So what does this mean? This means that at 0 comma, if I plug that back into my original equation, 0 comma 5 is an inflection point. So now I can draw a very accurate sketch of everything we've had so far. We've got -2 comma 21. We've got 0 comma 5. That was my inflection point. I'll do it in green. 0, 5. That's 21. 5 would be about there. And 2, negative 11. I know that it's increasing. Changes inflection at 0, 5. Have my maximum and my minimum, so there is the graph. Now, sketch the curve, label all stationary and inflection points. We're going to do it in the order that I like to sketch curves, but just off to the side, just to practice. I'm going to do the second derivative test right off to the side. So second derivative test, I'm going to find my first derivative, 4x cubed minus 24x squared. I'm going to find my second derivative, 12x squared minus 48x. I'm going to factor both of these. Okay. Right away, I can tell that 0, I can't tell from the second derivative test if 0 is going to be a maximum or a minimum, because my second derivative is equal to 0 there as well. I can't tell if it's concave up or concave down. But at 6, I know that this one right here, because if I plug 6 into my second derivative, my second derivative is going to be positive and concave up. I know that this is going to be a minimum. Okay? That's just my second derivative test. So with that amount of information, my second derivative test tells me that 6 is a minimum, because the first derivative is equal to 0 and the second derivative is positive. But if we were going about actually the process of completely graphing this, we would have, just like over there, started off with our first derivative, set it equal to 0, and factored it just like before and found out x equals 0 and x equals 6, and plug this in. And from our first derivative test, we're going to notice something at 0. When I plug in something less than 0, this is negative, decreasing. When I plug in something between 0, again, I'm going to mark this over here. We're plugging this into our derivative. When I plug in something between 0 and 6, like a 3, it's still negative. So we can see that that's not a maximum or a minimum. It's going to be a stationary point of inflection. And after 6, it's positive again, so we could see that it's a minimum from our first derivative test. So if we're labeling things, we've got the point 0, 0. As a stationary point of inflection. And 6, some big numbers here. What's 6 to the power 4? 1296? Oh, I don't know. That's That's what came to my head right away, but I don't know if I trust that. Yeah, it is. Okay. 1296 minus 8 times 6 cubed. Negative 432. What a beautiful point. And we know that that's a local min. And then from our second derivative, which we already figured out over there, was 12x times x minus 4. Set that equal to 0. And our number line for our second derivative was 0 and 4. Plug in something less than 0. Both of those will be negative, meaning this is concave up. Between 0 and 4, it's negative, concave down, and after 4, it's positive again. So we know that, well, we already knew that 0, 0 was a stationary point of inflection. Now we can also say that 4, comma, and again, we'll have to plug this into our calculator. 4 to the power 4 minus 8 times negative 256 is an inflection point. Yeah. Yes. Well, a stationary point means our derivative is 0. And a stationary point of inflection, which we're going to graph it right now and see it. The last thing that I probably should have done that I didn't do at the beginning is, could we find x-intercepts for this one? I think we could find an x-intercept quite easily. Set y equal to 0, factor out an x cubed. Can you see that you'll have an x-intercept at 8 and at 0? Okay, now the stationary point of inflection. It is a stationary point. Okay, when I go to graph this, we need to label some very big points, right? We've got 4, negative 256. We've got 6, negative 432. And we've got another x-intercept at 8. 1, 2, 3, 4, 5, 6, 7. 8, 0. And 0, 0. Those are our x-intercepts. $100, $200, $300. So I chose a scale based on the points that I had. I knew that I had to have 6, negative 432. So I'm going to go to that point, 6, negative 432, and label it. I'm going to put this 0, 0 in blue as well because it was a stationary point of inflection. And then we were also told that we have another point of inflection at 4, negative 256. So I set my scale up, and then here I'm just sort of estimating approximately where those values would be. I like to draw my curves based off my inflection points. So 0, 0 is an inflection point, and 4, negative 256. So my final graph here in purple, this part has to be concave up. Between 0, 0 and 4, negative 256, this part needs to be concave down. And then after 4, everything else, woo, that's, no, okay, I better, gotta try again. That was a fail. There we go. I need to get down here, concave up. That's better. Whew. And go back through that X-intercept. So when you're talking about 0, 0, stationary points you find from your first derivative, how come this was an inflection point? Well, at this point, if I drew a tangent, it would be completely flat. It flattens out right at 0, 0. But it's not a minimum or a maximum because the graph kept decreasing. But it does change from concave up to concave down, so we call it a stationary point of inflection.